Now, a few words about the speed of sound. The speed of sound in fluids and gases may be calculated using this equation: V equals square root of B divided by rho, where B is the bulk modulus and rho is the density of the fluid. As we know, fluids includes liquids and gases. The bulk modulus can be calculated from this relationship. Whenever there is a change in the pressure in the fluid, the change in the pressure divided by the fractional change in the volume, delta V divided by V, is called the fractional change in the volume. This is equal to the bulk modulus. And the minus sign here is just to tell us that when you increase the pressure, the resulting fractional change in the volume will be a decrease. So an increase in P is associated with a decrease in V, different in sign, so we have this minus sign here. In general, the velocity of sound for fluids is calculated from an elastic property divided by inertial property. Because the bulk modulus is an elastic property, it depends on the elasticity of the medium, and rho depends on the mass per unit volume, density mass per unit volume, which is the inertial property. On the other hand, the velocity of propagation along a string is determined from the tension force between the two ends of the string divided by the linear mass density. Okay, so we have two velocities to talk about: the velocity of propagation along the string and the velocity of oscillating up and down for the various molecules of the string or the medium. For longitudinal waves, the velocity then is determined by elastic property divided by inertial property. We have this equation for gases and liquids. We have this equation for solids. The velocity of sound in solids is equal to square root of y over rho. Y is the Young modulus. Young modulus is similar to the bulk modulus, but this is for solids, while bulk modulus for liquids. Again, Young modulus is related to the change in the pressure divided by the fractional change in the length, for example, of a string. So these equations allow us to calculate the velocity of sound. In this table, we see the speed of sound in various media. For gases like air, the speed of sound at 0 degrees Celsius is 331 meters per second. At 100 degrees Celsius, it goes to 386 meters per second. We see great change. As air molecules gets hotter and hotter, gets more kinetic, more energetic, the speed of sound gets better, gets higher. We have these values for other gases like hydrogen. It's at 1286 meters per second. The density is less there, much less than air. For helium, 972. Again, density for helium is much less than air. For oxygen, 317 meters per second. Air is composed of oxygen and nitrogen, so it's the same order of magnitudes. For liquids, just to get an idea, in water, it is 1493 meters per second. For seawater, it is 1533 meters per second. To complete the picture, for solids, the speed of sound is much higher than that for liquids or for gases. In aluminum, it is 6,420 meters per second. For steel, 5,950 meters per second. Usually, we do not expect the students to memorize these speeds. Just you can refer to any physics textbook. You will find them listed there. But it's good to remember speed of sound at room temperature. At room temperature, speed of sound in air is about 345 meters per second, between these two numbers here. This equation allows us to calculate speed of sound at any temperature. We take the speed of sound at 0 Celsius as a reference here, 331 meters per second, and you multiply it by square root of T divided by 273 Kelvin. So the temperature has to be converted to Kelvin. So at 20 degrees Celsius, 20 means 293 Kelvin. We substitute here 93 divided by 273. The velocity of sound in air at 20 degrees Celsius is 343 meters per second. Which of the following actions will increase the speed of sound in air? Decreasing the temperature, increasing the frequency, increasing the air temperature, increasing the amplitude of the sound wave, reducing the pressure of the air. Based on what we learned so far, the correct answer here would be increasing the air temperature. Increasing the air temperature will increase the velocity of sound in air.